First, hold on. Everybody thanks Alex. He sent like at least 3 or 4 emails. Make sure the guys was the first one to present. So he spent some time doing it. All right.
We are Team 5. I'm Ryan.
I'm Tyler. So our project is to recreate or replace tennis ball kids. So what their responsibilities are at the end of the match, there's going to be tennis balls that are near the net, and the ball kids would be around there to grab it, so the players don't have to grab themselves and take it away from the court and then bring it back to them. So our car is to do their job and identify the tennis ball at the net, track the path towards it, and then also retrieve the ball and come back to the home base. So that's the base of what we wanted it to do. If we had any more time, we wanted to somehow relay the ball back to the player and have obstacle avoidance. So if it's not on one side of the court, it'll avoid the net and also avoid the player if possible, but that's only desirables.
So here's our motivation. Our first motivation is to revolutionize or just add something new to the sports industry. Decided to go with tennis because tennis is a great sport.
That's when we got to play tennis now.
When players hit into the net, there's a lot of room for more efficiency because the retrieval of the ball is limited to how fast a human can go get the ball and come back. An RC car, or at least maybe a more advanced robot, can do that much quicker. An example of technology that is already implemented in tennis is Hawkeye ball detection. Basically, in some of the larger matches or tournaments, there's 10 cameras viewing the court, and it tracks the ball continuously. They use it basically to see if a ball is in or out, if it's a hard call. It's usually, the average error is around 3 millimeters, so it's pretty accurate. And lastly, some tournaments can get really hot. The Australian Open a couple years ago reached 111 degrees Fahrenheit and caused like 9 players to withdraw from the match because it was too hot. So, for instance, the kids that are working the event, it might be unsafe for them to be in that heat.
Yeah, so as part of it, we wanted a way to grab the ball. So we actually kind of went through a lot of iterations of this to try to get an active mechanism to go up as the car drives, grab onto it, and actually have control of that. We tried a roller design that was to sort of spin and roll it in. We tried 2 versions of a grabber design, and in the end we decided that it was kind of just either infeasible because our motor on the roller design wasn't powerful enough. We were having some issues getting the servo to work, getting the servo breakout. So ultimately we went with a passive design. That was just a scoop that had some Velcro on it, and that was actually really nice to drive up to it, and just once it bumped into it, the Velcro grabbed onto sort of the hairs of the ball, and it had good control of it, enough to drive around with it and bring it back to its location.
So you could attach to the Velcro before the ball rolled out of it? Nice.
Yeah, it just kind of needs to come in contact with the ball, and it has enough grip to hold on to it.
So that's for the mechanical side, and for the software side, generally what we went through over the entire process was we wanted to do the GNSS and the camera first off. So we wanted to have them running at the same time, but for some reason we had an issue where if the GNSS was on, the position was tracked, but once the camera was turned on, the position was lost and the location of the ball was also lost. So for some reason we tried, and we're not able to have them both working simultaneously. So then we tried going to the IMU of the GNSS and trying using that at the same time as the camera, which kind of worked, but the GNSS was unstable and the error was very high in accumulation. So that wasn't accurate enough for our little target that we had to go up to, and so we had to try something else. And so we went off to switch out the GNSS with the odometry and change the GNSS IMU to a seed IMU, and that was able to calculate the position of the ball with the camera on as well. So we weren't having too much of an error, and it was able to track a path towards the tennis ball.
Yeah, here's a list of kind of our main software demonstration package that we made. There are like 5 main codes. The first one is the finance ball code, which will send a YOLO model to the camera, and then it detects the tennis ball, and then it also subscribes to the location topic. So it transforms the location of the tennis ball in the camera frame to a global frame, and then we publish the global frame coordinates of the tennis ball to a Team 5 ball topics. And then we have the follow ball.py, which is the most important code that subscribe to the ball location and also the location of the car, so you can plan a path and use LQR control to track the path and retrieve the ball, and then it generates another path and go back to the base location. Then we have the UDOM.py, which is a custom UDOM node that we made. So we completely replace the UDOM node that already exists in the Docker container. But it's just first order orders method. So we integrate the linear velocity, and then we use IMU for orientation to get the localization of the robot. And then we have the plot stuff.py, which just the name of it is just for plotting things. And then we have simulation.py, which we use when the localization wasn't working well. We use the simulation.py to simulate the car and then simulate the situation where if the localization is working perfectly. It's just for visualizing the control and designing the LQR control. And here's a video of the odometry localization.
So you're using the VESC process for that?
Yeah, using the VESC, because the VESC it outputs the ERPM of the motor.
Yeah.
So we use the ERPM, convert it to speed, and then we use the CIMU for orientation. And just numerical orientation.
And then you just convert to find out there was X number of clicks to the diameter of the wheel?
Yeah.
Did you say that? Cool. This guy spent a lot of time on this, isn't he? Very cool.
Could you filter magnetometer and gyroscope data to get the orientation? What do you measure from the IMU?
Or use the gyroscope.
Just the gyroscope? Or just directly the gyroscope?
With some offsets.
No, he used the gyroscope, but then he said that for the odometer he was using the VESC ticks and find out if it was in a straight line, how many ticks was for the 2 pi r line.
Yeah.
I say, hey, this was like about a half meter. It was pretty cool.
Yeah, then there's a video of the ball retrieving. Struggling to press it enter, but it started. Goes to the ball and it should take it.
Yeah, I'm glad, surprised that the ball just didn't roll out. Nice.
So although we did meet up all our marks and in what we set out to do, we still did have some shortcomings on some features that we wanted to implement. Given more time, we think we could have implemented at least some of these things. The first one is continuous ball detection. Obviously, ideally, it would be ideal for the car to be able to see the ball be hit between players so it knows where it is at all times. But that would be very difficult to implement with the amount of time we were given. Another thing we wanted was to be able to relay the ball to the server. In between points, the server needs to get new balls to serve it again. That's something we probably could have done if we had like a week or two. We set out to have the RC car be quicker than a human, but we spent most of the time just trying to get it to work rather than having it be faster. And when we set out to have a more advanced mechanism, obviously, to pick up the ball. Ideally, pinch it and then lift it off the ground, but that just seemed a little out of our scope, so luckily the plow mechanism worked really well. But a downside to the plow mechanism, the Velcro holds onto the fibers of the ball, and whenever you take the ball off, it rips off the fibers, so it deteriorates the ball a lot faster than just regular playing.
So here's our Gantt chart. As you can see, kind of a large portion of it was the CAD design of those mechanisms, as well as just time spent on the tennis courts actually testing. Whether that was going through all of our iterations of how we're trying to do localization.
Did someone went there and say, what the heck are you guys doing?
There were people that would give us glances
Yeah.
of like, they're looking for a tennis court to play on. They're like, what are they doing?
Yeah. One time we had to leave because there were like 4 people that were like, "Are you guys using the court?" I was like, "Not for tennis, but
All right. Thank you.
Thank you."
You guys don't have any?
I'm David. I'm Alex. Miles. I'm YY. So what we wanted to do for this project was create a short bot autonomous vehicle that would pick up objects and deliver them in different precisions. The parameters for what we had is 3 objects in 2 locations, and the pass had to be somewhat simple to object between point 1 and point 2. The key differences, there was a short bot before. The key differences are that we were using GPS instead of line following, and then we included path optimization. So the lures that we were going to do is with the Oak D camera, we're going to use it to identify the objects, and then that's going to give us the path that we're going to have. So we have 3 different shapes. The circle correlated to drop off location A, square for location B, and a triangle is in case we got both objects with us. And then we also include static obstacles that we're going to use to avoid them using GPS.
What is the triangle? Oh, just.
Triangle is point A and B in case we have to go to both.
So to identify object types, we did a shape detection AI model. So we deployed to the OpenD camera with RoboFlow, detect circles, squares, and triangles. And we made sure that between the 3 different classes, we had a balanced data set of images, because we found that when we had too many images for one class, for instance, it will have problems detecting shapes. So we had like 175 for circles, 171 for squares, and 205 for triangles. And we also ensured that each class had like a diverse data set for each, like for instance, the combination of colors between the shape and the background. So, and also we made sure that the shape had varying orientation. So like for instance, the square, if it was slightly tilted, it's not gonna have problems reading that as a square because it was maybe a little bit more like at a certain angle. So we just made sure it was nice and diverse. And then here's the precision of our model. And we deployed using a .py file in the donkey cart framework. So here are the results for the trained AI model. It detects shapes precisely. And it's detected, we were able to detect the shapes individually as well as all 3 at once. And however, there were shapes detected in the environment that were not present at low confidence intervals, but we just wrote in our code to ignore any detections below 85% confidence, so anything above that will then cause the path planning to execute.
So in terms of executing the path planning software, these are just the basic inputs and outputs. So you need to define an origin within the longitude-latitude frame so it knows precisely where you want to do your local UTM coordinates. So we need to supply that. We're assuming the pickup is at the origin, which would be 0, 0 in the local frame. We need a heading because donkey car, their local frame is relative to true north. So if you were to reset the origin and you didn't define your y-axis in the local frame to be directly true north, it would generate within the first quadrant, when in reality it should be, let's say, in the 3rd quadrant. So you simply define a rotation matrix giving your heading from true north and rotate the frame accordingly. So it needs to take in that. The drop-off locations can be in the local frame. The objects to avoid, the static objects to avoid, and the relative size, which are estimated as rectangles. In the local frame, offset value, you want to be away from static obstacles because you don't want to be hitting directly on one of the lines. And then car dynamics values like speed and minimum turning radius. And the outputs is going to be a CSV file of GPS coordinates. So the general procedure for how we got this to work is we originally wanted to do it in ROS2, but we ran into a lot of problems with GPS in ROS2, trying to get it to work, as I'm sure many of the other presenters here will talk about today. So we pivoted back to Donkey Car Framework, where we simply just added a line of code in the manage.py file upon running before it runs any of its code to call a master path planning function that we defined. And upon doing so, it runs the object detection on the camera, and then you see in the if statement, if it's above a certain confidence, then it will go and print that into the command window. Then it will run the path planning and call that with all of the config values that you defined as the inputs. And then from there, it saves it as a CSV.
And that CSV is what you use for your donkey card.
And so then
you
it
just
will-
pass it through.
Yeah, it'll just read directly from that CSV.
Cool.
So to find the most efficient path, we start by looking at every possible order of drop-off points. We generated that using permutations. And then after we find the different orders, we find the total distance of each path. And then we take the shortest distance and move on to the next step. So once you have the shortest distance, you check to see if any of the line segments intersect with the rectangles, and insert new points to kind of go around the obstacle as needed. And then that happens recursively to make sure you're always missing the entire obstacle and not just cutting one corner at a time. And then once we have the final points, we use a cubic spline to interpolate kind of a smoother motion between the points, like the picture shows. And then we generate equidistant points along the spline to spit out into the Donkey Car CSV. And that follows what we observed in the files that we recorded earlier in the class. And so here you can see the conversion to GPS coordinates. So Donkey Car takes in UTM coordinates in a local frame. Like Miles mentioned, that's defined by heading from true north. So the user defines the GPS origin and the heading angle, and then we do the math to rotate that into what we need and account for the local origin. And then we generate the CSV file at the end using the correct frame. So here's an example of kind of the steps. So you can see all the rectangles here, each one defines kind of an obstacle. So not necessarily an obstacle that's rectangular. So if you have like a weird shaped obstacle, you just have to have like a bounding rectangle that covers the area that you want to miss. You can see here also that it doesn't perfectly follow the edge because we want to have some offset to have a factor of safety versus you cutting right by the obstacle. And then in the second picture there, you can see after we've generated the points, it does the spline interpolation between it. And then in the third picture, you can see that's rotated to be in the third quadrant to account for the direction we're facing.
Quick question. So on that two extreme curves, I guess your lower left corner and the right, can you actually do that?
So it depends. We originally wanted to use Dubin's path, which we had talked about, which specifies a min-turn areas. It became very problematic because you have to specify poses at every point. So we opted to just go to simpler paths and do the spline and make sure that given that frame, that turn should be around half a meter, which should be within the car's capabilities. Obviously, if that was a scrunched y-axis, then it probably couldn't make it.
Okay.
So that's something that we want to improve on in the future, 100%.
And so here's a simpler example, and then this is what we actually tested in real life. You can see here there's just two obstacles, and then you can see again how it gets interpolated to the spline, and then the equidistant points are generated, and they're adjusted for our heading, since we were facing pretty close to south on the track next to EB1.
So how well did we do? We wanted to see how accurate our data was before we tried to give it to Donkey Car. So we simply did what we did 5 weeks ago, and we ran Donkey Car and manually drove the path and then compared the points. So our optimized path is in blue, and the recorded path is in orange. Obviously, Conquer has some errors. That's GPS errors. Didn't really get around that. But I think we did pretty well. Matches pretty well, and the rotation angle is good. So this is the actual path that we set up to physically realize it. So pickup we can't quite see, but it should be about right there. Our first obstacle, we wanted to make sure that it was in direct line to drop off A. No obstacle between drop off A and B, so it should be a pretty straight shot, or after the spline, a curve. And then again, we have one going from B back to the pickup, so we should see that our car goes around them correctly. And here is a performance demonstration. I'll try and narrate the video as best as possible. It's a little hard to see what's on the screen.
Stop running.
Perfect. Yeah.
Yeah, maybe if we take forward presentation mode, but if you have the file, so we can wait. No stress.
Sorry, guys.
Actually, someone sent me a mail this morning. Your students are day and night here, very nice. So I was seeing you guys. Yeah. They like your class? I say, yeah.
Day and night for sure.
I remember that guy. He was cool.
Oh, he can talk to you?
Yeah.
Uh-huh.
Which guy was it?
I don't know, I didn't get his name.
Yeah, he's from the CAP, he's from the Corporate Affiliate Program.
Oh, really?
Yeah,
Interesting.
he sent me a mail.
No, not the cost.
Anthony, thank you. Yeah.
Here we go.
Don't mind the reflection. So what I'm showing here is that there's no CSV file called sortpath.csv. That shows that we're not just
Playing back.
faking
yeah.
it, right? So we start the object detection. It doesn't do anything until I show it a triangle. Remember, triangle goes to drop off A and B. I show it, confidence above 87%, we're good. Triangle detected, path created successfully. So when I reset the origin, this we have to do manually. We did not know how to emulate controller input. So we're doing that manually. Origin reset, and it should load sortbotpath.csv, and we run it. It's going to dodge the first obstacle. And comes fairly close to the drop off in blue up in the left hand corner. Goes to the next drop off, which is right there, pretty close, within about a meter, comes back and just makes it past the last obstacle and back to the origin. We chalked that up to error in GPS. That's about as good as we could get it. You can mess around with the origin and bring it back and forth, but we're within about a meter accuracy is about as best we can.
Alright, so here's our Gantt chart at the beginning of the quarter. So we were gonna also possibly do a hardware, but in the end of the day, we just decided to go focus. That was a reach anyways. So as predicted, we just decided to stick with software. And this is what ended up being more of our Gantt chart where everything kind of overlapped because there was a lot of like...
Everything got pushed in.
yeah, especially with the ROS problems, so then just started going to Python costs.
That's real life.
That's
right?
how it goes, exactly.
This is exactly how you have to remember this when you get a job and you find something, there'll be this big crunch in the end, so try to push as much as you can in the beginning. And what you don't know, we don't know. As long as you're going to have some buffer time for the things that you don't know.
But for required things, we were able to detect the object shapes, the 3 different types, and then we're able to avoid the obstacles and deliver to those drop-off locations. So for the mandatory, we checked all those off, so complete those efforts.
Isn't it funny? Because the MAE students, they now focus on the soft aspect of it. Huh?
Yeah, that
You-
was a
you-
game changer.
Yeah, we never figured out in this class, oh, it's mechanical engineering class, we're going to actually spend the time on the software, but you learned something, that's good. All right, everybody. Nice.
Thank you, guys.
Thank you.
I'm Candice. I'm Matt. I'm Mohan. And this is our final project presentation.
So just to recap, our project is so basically trying to detect low voltage, and then once it reaches low voltage, it basically use Google Maps API to navigate to the charging station. And our stretch goals are self-parking and self-charging, which we were able to get there. And the part that we are using is an Arduino Nano, a GPS for navigation, and also a some things inside the truck.
So we can divide our project into 3 parts: detecting the low voltage, self-navigating on GPS, and then parking. So starting with low voltage detection, we created a circuit. It included a voltage divider that connects to the battery JST connector. It goes to an Arduino Nano, which is connected to the LCD screen.
Just a moment. So if you guys will pay attention during the presentation, why did they need that voltage divider anyway? Anybody?
Because they need to be between 1 and 5 volts for the Arduino, but our battery is a lot larger than that. So the voltage divider allows you to drop down
Very
to
nice.
a smaller range and then get a percentage of that.
Very nice.
And this shows the first 3 hardwares. We made a JST cable to connect to the battery, which connects to the voltage divider on a breadboard, which is read by the Arduino Nano, which then communicates
Totally MAE design. Yeah.
to an LCD screen on the left, so that the driver can read the voltage, and a passive buzzer that plays a song when the low voltage is triggered. And this is just the Arduino software code that we wrote. It continuously checks for low voltage, transmits that to the Jetson, and then plays a song once it's triggered. So the first part of this video will show how the low voltage was implemented. So as you see, it starts at around 14.8. And then the voltage is continuously tracked. Can you hear it? So once it reaches low voltage, the LCD changes, and then Pirates of the Caribbean starts playing. So that's the low voltage part.
So for our GPS, our goal is to navigate to a parking spot after we detect low voltage. So we modify manage.py to add a bit for GPS functions, and then we convert the latitude and longitude coordinate to UTM coordinate for the donkey car to read. And then we also acquire current GPS position for the Google app later on. And then we implement the Google app API to automatically generate a map from the current location to the charging spot, and then avoiding any grass area in between. And then the car will automatically stop within a range of 0.005 degree of the charging station. So here shows that we gave a parking slot location to our goal, and then when the low voltage is triggered, the Google App API will automatically generate a path from the current location to the destination. And then for Google API, we kind of have to spend some money. So here shows the cost that we spent. It's only $1.38.
See, I'm telling you, call Elon Musk, see if they can save some money for him. Huh?
So here's the continuation of the same video. So after the low voltage is triggered. So we press the button and we'll start going. And then only cut a little bit of grass, which is pretty good. a little that sign right there as a parking spot. And I actually push close to a range and that will automatically stop.
And then for our code, in the manage shop high script, we basically have three definitions of three functions. Drive and check voltage is going to run simultaneously, so at the beginning of the script, when you run it, drive is going to run constantly, which outputs the GPS location and coordinates. And check voltage will be running constantly as well by subscribing to the Arduino to check if it's low voltage. And when low voltage is reaches, which is around below 14.8 volts, then it will play music from the Arduino script, and then it will call another function, which is the Google Map API, which will get the latest location from the drive function, and then it will upload the coordinates based on the current location to our pre-designed destination, which is our parking spot shown earlier. And then after that, we convert the units back to from longitude to latitude to UTM to upload it to donkey.csv. And then afterwards, after the donkey.csv was created, we then press the button to initiate the path to follow and to navigate to the parking spot. And it automatically stops within the area threshold.
So parking is one of our nice to have goals, and basically we wanted it to either parallel park or do lane parking, and it would see the yellow caution sign that we just got for pretty cheap, and then it would park about 1 to 2 meters off from it, and it's like this. We ran into some issues with it, and a big issue is just with GPS, where basically the car had to face a correct orientation or direction for it to trigger, and due to like the inaccuracy directly of the GPS, as well as having to tune PID control, it wasn't the most accurate, and also just the voltage meter would sway a lot, where like it wouldn't be a consistent reading throughout, so it could either trigger it early or just like read it off.
Why do you think it was that voltage fluctuation? Anybody have a guess? Was the car stationary or was the car moving? Again? Think about it. Like, the whole point of this battery has, remember that C that you have there, that means I can discharge really quick as soon as you give some gas, right? And then I can give you power. But I don't have to have a big battery, right? I just have enough just for you to take off or do an acceleration. That's why that fluctuation come around. Obviously, that other alarm that we have, take that in consideration, just average voltage versus just like the peak voltage. You bring your peak voltage, right? Instead of have an average, right? Okay. Does that make sense?
Yeah. And here is our grant charts.
I don't know why we thought we would finish before week 10.
Yeah. Oh well, you would finish the class early, right? Okay, nice.
Should we start? Okay, so we're team
Well,
one.
let's try it again. Take two.
Hello everyone, we're team one, the Autonomous Tour Guide Project. I'm Charles.
I'm Jay. I'm Eric.
All right, take three.
Yeah.
I disconnected from Zoom.
This is just Zoom's not updated.
You don't have it memorized?
Is it?
Yeah, so we seek to create a tour guide. It would seek out a walkable path and using GPS to navigate. It would also use the camera to detect the user, detect how far they were, and then adjust the throttle to match their walking speed so that they could leisurely walk around the tour, stop if they want. And in essence, it would look like the user putting on like a lanyard of some pattern that the camera detects. That's how it calculates.
So in terms of what we actually accomplished, we hit a couple big needs that we needed. Of course, earlier on, I'm not sure if you remember from the other presentations, LiDAR was a big need. That will come back later. But we were able to hit all the big milestones for the core parts working on. Is it to detect a tourist marker? Is it to specify a route and then adjust the tourist speed or its speed to match the tourist? And then finally, you can use GNSS for all the routing and path. So we're able to hit all those big accomplishments. However, for the goals that we wanted to hit and we didn't, there was voice controlled UI. That was a long shot from the beginning. The Google Maps API integration, once we were stuck with, we were trying to work with the original GPS nodes and GPS programs from Donkey, trying to then mold that with a Google Maps at the same time. While we were still hitting too many errors with the initial version, we just didn't go for that. User speed adjustment was originally a want. We were able to hit that. It was great. And LiDAR, we did not get to at all. Everything else is way too much, so that was dropped.
Okay, yeah, these are the key components on our robot. Basically, we are using the OAK-D Lite, which is the camera, and the GNSS as our inputs, processing it through JetSync and partly in the edge computing with the OAK-D Lite, and we are controlling the vessel.
Yeah, so we soon realized that ROS2 is the best framework for our purpose as we need continuous output from some things which affect actions of another thing. So this is the overview of our whole project. In ROS2, we use the Fusion Engine node to take in data from the GNSS and publish that in lat longitude. We have the GNSS, and then Ntrip corrects that data using the Polaris correction that we were given. The GNSS nav node takes in that latitude and longitude, converts it to UTM, which Donkey uses to navigate CSV file. We use a preloaded CSV file in UTM that the user can specify. And then we have path planning algorithms in there that we use and recycle and modify from Donkey, which publishes steering angle, while the throttle is controlled by output from the camera model, which is stored in the camera distance node. Yeah, so our first step was being able to uniquely identify a user. So using a RoboFlow dataset that I know a lot of other groups use, but it's something that doesn't occur naturally in nature. So going out on a tour, it should be able to hone in on a checkerboard pattern. An image, this is the first time we deployed it to our phone in order to test that it only detected a checkerboard and nothing else. And then we needed to get distance from the identified pattern to the robot in order to set a certain distance that we want the robot to be at to match the walking speed of the user. We noted that, like Luxonis had examples where they could detect objects of many classes and output in spatial coordinates X, Y, and Z how far you are, which is the Z coordinate depth, using OAK-D. So we wanted to use snippets of that, but only to detect like the checkerboard pattern. So if you go to the next slide, we're able to hone this while like combining our model from RoboFlow to only detect checkerboard pattern and then publish that distance continuously at about like 5 hertz, which was good enough to have the robot stay in the range of the user and control the dog.
Yeah, so once we have the distance, we are publishing that as camera distance, so that's our topic, to VESC node. And we program the logic directly into the VESC node. So it's in the callback. Basically, we're saying that if the user distance is between 0.5 meters and 3 meters, we will set to our faster throttle, which is 0.4 of our max speed. And then if the user is even close, it's backwards. Switch fast throttle and slow throttle. If the user is, no, this is right. If the user is closer, it will, is this right?
Yeah, it'll speed up.
It's backwards, right?
Yeah,
It's backwards. If the user is farther away, it'll go a little slower. If the user is too close, it'll want to go faster. So
The other way, right? If it's
The other way around.
it's farther, go faster.
yes.
Okay, right.
The slide is going, flip it. If the user is close, we're going faster. And basically, we don't need a third line saying if there's no data, no throttle, because we are subscribed to distance. If dist stops publishing, then the callback never runs, so throttle never goes off.
is just a video of the camera detecting it, gauging the distance, and being able to adjust the throttle continuously.
And how do you know?
We have a visual output on.
No, so you're going to show to us that we, let's say, 0.5, and then there's an output coming out?
Yeah, it's hard to tell from the video, but when it was closer, it was going faster, and then it slowed down as it backed up, and then when we removed the checkerboard, it no longer detected, so it said
If
RPM
you turn the
0.
sound on, you might hear it.
Yeah.
But it's hard to see.
That's right, so we trust you. I'm just trying to see if you're confident on that.
So the last part was bringing all this together with the GNSS navigation. So we thought originally we could run the normal Donkey Car stuff that we'd already done, I believe in like week 2 or 3, and just have that CSV path and run that in tandem. The problem with that is running the ROS2 communication that would control the VESC and Donkey that also is trying to control the VESC, trying to run those two in parallel, even though the Donkey Car had an option when running to have a user-controlled throttle. So essentially, it only controls the PID correction for steering and not the throttle at all. We tried using that as a crutch. It didn't work. Essentially, both Donkey and ROS were both sending exactly opposite commands to the VESC. So it didn't crash, but it didn't run. So essentially, when we tried it, it would start, stop, continuously because it would be getting 2 commands immediately. From ROS2 node, it would be getting the command of setting it a certain RPM for moving forward, and then it would also immediately be getting the same command from Donkey to have 0 RPM because there's no throttle input. It's supposed to only recognize the joystick input. And we didn't want to try to pivot into creating a virtual joystick in ROS and then feed that as an input that way. So this was the nail in the coffin for us trying to have a bridge between normal, just background Python running, and then ROS2 nodes. So this kicked us into doing the GPS only ROS. So from that, we had to grab additional snippets from manage.py, other Donkey files, and USSD robocard nav2. So some of the examples up here are the la.py, path.py, and VESC client in addition to transform. So VESC client is one of the nodes that generates a VESC object from that generates a VESC object that's used in the VESC node from UCSD nav. And then the LA, path, and transform are all used for navigation calculations in Donkey. So we were able to pull from those and then adjust that to work within our framework. And the last step was getting the GPS navigation working. So we had Fusion Engine Driver, which published GNSS data. We could get that GNSS data. We could convert it to UTM, but we wanted to try to get it as accurate as we possibly could. So we tried to use Ntrip client as some other teams. We worked with, for example, today on getting Ntrip working so that it could correct additional data from Fusion Engine, correct it, send it back, and then Fusion Engine could publish that on top of what we were already using. And then, of course, we would use the CSV that we already generated in document to guide the path. So our final GNSS nav node was a subscriber and a publisher. The whole point of it was to get the latitude and longitude, normalize it, and then plot a, so we would reference the original path. We would be able to identify the closest 2 points and use the rest of the navigational algorithm from Donkey in order to get a correct steering angle. Where's the vector you want to be? What's the difference between your position and that? And then we would publish that to the VESC and adjust it to meet the steering angle requirements of either between 0 and 1 as a flow. And after a lot of trial and error, we got it working loosely. The biggest issue we had was we had a lot of issues converting the steering angle for some reason. We tried to use it the exact same way it would have been done in Donkey, just using it within our framework, and for some reason, all of the data types did not work. We had to constantly retransform our path CSV and to get it away where we could get the correct angle. We're not sure why it worked like that, but
yeah, like we had like the CSV that Donkey wanted was like a list of tuples like x, y coordinates and UTM for GPS, and we did that, but it didn't.
Yeah, it did.
I don't think I did.
I mean,
The video's 20 minutes.
It looked good.
it's This is a slow-mo video.
Okay, it's 3 minutes long on my side. 3.
All right, so now I get it to why you say you're gonna slow down when it's far. I thought it was following you, but you follow the robot. That makes sense. Okay, that makes sense. All right.
Maybe that's on me.
I mean, just assume that this was part of your plan. Good.
Yeah, and for reference, this CSV reads origin as EB1 and then the destination as the structural engineering building right there.
All right,
The one with the design.
we got it.
Yeah.
That's on me.
Aesthetic.
I can't speed it up anymore, unfortunately.
Just skip around.
I can skip around. So this was our only test that we got to work. One thing that was nice is that our PAD was able to overcorrect and readjust. It had, as you saw in the beginning, it basically did a full circle. It was able to recatch the path, follow it for most of it. It went off again, got stuck. We just moved it back on concrete, did another big loop, was able to catch the path again, and was able to work forward. So while it did work for our intended purposes as a very rough proof of concept, that's one of the things we'd want to fix. Like, we'd want it to be able to match the path following, at least from the GNSS donkey cars.
Okay.
It's to the very end.
So that's where it got stuck, the grass.
And we picked it up, just put it back on the concrete. And pretend we got here in 4 minutes. Not minutes.
Yeah, so the reason why we think it took 4 minutes is not super precise data from GPS, as well as PID tuning. We could have further tuned it, but also, like we said, like the pathfinding algorithm, we only looked ahead to one point, but if we had more time, we would have made a more sophisticated pathfinding algorithm to like take into account further points instead of just trying to hit each waypoint, which is what it was trying to do.
So if we had another week, obviously we'd want to fine tune the PID and navigation. But the other thing we'd like to add would be just adding a LiDAR node. Basically, if it detects any objects too close, then we would like to override the desk and stop. Further, even more time, it would be really nice to be able to identify objects moving within and out of range with the LiDAR, and then be able to either navigate around or have a better way of detecting possible obstructions earlier than if it's just right in front of it. But that would be for more time. In addition, we'd also like to just find other ways to path instead of the CSV that we were using. While it works in concept and in practical application here, it just ended up being too much of a hassle trying to convert that into the format that we have. And this is, I think, the most emblematic show of our entire project, where we had a very nice Gantt chart at the beginning, and then it completely blew up. We've been working on this, I didn't say it about the past 2 weeks. And yeah, that's our final Gantt chart.
Yeah,
There's a
yeah.
lot more below and a lot more colors.
That's a lesson on here, so for everybody. That's the idea behind it. That's how we do this exercise. All right, thank you.
Hello, teammate.
Number one, no stress. This is supposed to be fun. I hear you guys a little bit stressed. Just show the work, show the effort. That's good, right?
I'm Aaron Marshall. And I'm Eric.
Nice. Fast.
Okay. So our project overview. So we for sure wanted to have a hitching mechanism with communication over ROS, GPS navigation by dividing the workspace into trapezoids and then using nodes of each one to create a path with guaranteed obstacle avoidance, and then object delivery at a specified location. We wanted to implement computer vision to decide what packages to drop, we can get to it, and we wanted to implement LiDAR and we can get to it. So, the GPS. So we spent a lot of time getting the GPS working. We got Entrep working. It publishes, but the corrections are not as frequent as we would like. So it gets it. So Q1 Runner, I'm convinced Q1 Runner is not actually correct, because that one's accurate to within like 5 meters. It's horrible. It's most definitely not stuff on center. And then if you use Entrep, you can get it accurate to around me. I haven't found, if you leave it in one place long enough, it'll get more accurate, but if you're driving, it's not good. But we got it better. And yeah, it's the same framework that T1 was discussing.
enter client Fusion Ninja driver. The documentation online is not complete, so we'll add that to our. And so we also included a pathing algorithm in the hopes that we would be able to plot a path for the car to follow and deliver the car to. It takes a large defined workspace, the coordinates that define the vertices of it, and any additional points that you want to define any obstacles within that space.
So, let me see if I get this. So, you have your basically your limit to where it's valid for you to navigate.
Yeah.
Then you say my object has this point, so then you basically want to link those points to become a no-go zone, something like that. Okay.
Yes. Yeah. And
So that polygons there is basically give some points, and then you link those points and tell this is an obstacle.
Yeah.
Okay.
So the valid workspace for the car to drive in is the blue area,
Blue.
and everything that's in white is defined as something with
No go.
And so once you have the valid area to work with, it's decomposed into triangles. And so taking the centroid of each of those triangles, you can get potential nodes to connect between the entire workspace. And then once you add a start location for, say, the car's position and a goal location where you want to go, you connect that to every centroid in the little C with these darker points on the blue area map out points the car can travel to. And so it will then, using a pathing algorithm, in this case we wanted to sort points by how close they were to the goal location at the end. It'll generate a list of those nodes that will get the car, ideally from the start location where it is to the goal location, traveling through those points. And so yeah, this diagram is just this is Warren Mall, and those large white obstacles are.
So which path do you? I can see all the possibilities. Tell me one more time.
Yeah.
Which one do you
So
choose?
it's
How do you
a little
decide which
difficult
one?
to see, but starting, there's an orange dot right
Yeah,
here.
I got it.
And then there's a green dot above that, and so any of these colored nodes, you can see the green dot will go all the way to that red dot.
It goes
on the
straight
other
side.
end.
Okay.
So yeah, I should clarify. The start node is on this left side.
Okay. Right.
And the end node is on the other side of the fence.
Got it. Okay.
Edges. So yeah, it'll travel along those edges to reach that goal node.
And then the final main component of our final project was, of course, the cart. The main goal for the cart was to have it hitched to the back of our car and then be delivered to a specified GPS location using the path planning that Timur mentioned, and then drop off the corresponding package depending on the final location. And all the framework for the cart and the whole mechanism was able to be made in ROS, a total of about 10 nodes being run at once, some of which were third-party nodes that we didn't need to design, like the VEST node that Team 1 was also using. That was provided in some of the packages in the Docker container, as well as the GPS nodes. We were subscribing to the GPS to get the corrected GPS coordinates using Metric and Fusion Driver. But we also had our own custom packages that we built ourselves, one for the cart and one for the Jetson Nano. The cart packages, given that since we were using the robot control library for all the hardware on the cart, that package was built in C, while the package on the Jetson was built in Python. There are a total of 2 nodes on the cart. One that controlled the initial rotation in order to latch onto the back of the car, and then one node that is
called once the car gets to the final location to drop off the servos. And then there's, if I believe correctly, about 4 nodes on the Jetson. One node that communicates initially with the cart during the latching mechanism. One node that determines the GPS pathing, and then a final node to communicate with to the cart again once you get to the final location to drop off the packages. There's kind of a sequence of events in our final project. There was the latching mechanism, then there's the path planning, and then there's the drop off. So for the latch, we initially wanted to get a error in orientation between the 2 vehicles, and then send that error over to the cart, and then have it maneuver the specific angle, and then latch onto the back. We initially wanted to do that using the reach goal of the camera and using the April tags in order to understand the orientation of the cart using the camera on the car. We weren't able to make much progress in that, so we had to drop it, and we pivoted to using the magnetometer on the IMUs. And then we also had to drop that given the lack of robustness of the IMUs that especially on the BeagleBone, they have their own built-in filters that filtered the gyroscope and the magnetometer data and the accelerometer data, and it frequently fell off of north, and you weren't able to get really any valid compass heading. So we eventually just pivoted to a design where the car would rotate in place, and the cart would rotate in place, and the car would try to slowly back up until it latched, which works somewhat well. Of course, it's not ideal. We wish it would be a little bit more comprehensive, but that's okay. And if we go to the next slide, then you can see a video of a demonstration. We weren't able to get the GPS path planning node in reality, so we just replaced that node with a demonstration node that just drove forward for 10 seconds instead of following a GPS path.
We have the node, but it's acting up. It just, yeah. Can't even get it to connect or anything.
So that latching was using the IMU, using the accelerometer. We were able to use it as an inclinometer to test, or using the force of gravity, we were able to tell how much the car tilted. So when the car latched,
so that was your load?
Yeah.
That you dropped that?
Yeah.
Mm-hmm.
When the car latched and tilted forward, we were able to sense it using the IMU, and that was the trigger to tell the GPS node, or in this case, just the accelerate forward node, to publish to the best node.
All right.
So here's our Gantt chart. Yeah, unfortunately we weren't able to do any sort of the computer vision aspects of the project. There were issues with trying to get certain OpenCV dependencies that weren't available to us, and it wasn't feasible to try and implement them. Or install them in order to implement them. In addition to more robust destination designs in terms of just driving there or having something instead.
And that's it. Thank you guys.